So everybody, let's talk about beta decay. So beta decay is another type of radioactive decay. And again, when an atom that is too big, it gets unstable. And sometimes in an atom like that, it can turn a neutron into a proton and an electron. So a neutron can actually become a proton and an electron. The electron is spit out, and that's called a beta particle there. So unstable atoms that are too big can undergo a second type of radiation called beta decay. And again, sometimes this can happen with a smaller atom if it doesn't have the right balance of protons and neutrons. So let's sort of try and picture that right here. So here we have a neutron, and it becomes a proton and an electron. Now, a couple important points about this. Let me actually scoot this over now about this proton and this electron. So the proton winds up staying in, if you get up here, the proton stays in the nucleus. So this new element, this new nucleus that's created, the proton stays in there. But the electron gets shot out at a high speed there. So the electron goes zooming out and the proton stays in there. So the name again for this is beta decay. And so we call this a beta particle. Sometimes you'll see the symbol here for beta, the letter. This is the Greek letter beta. It's a lowercase beta, and it's basically a B there. Sometimes you'll see it written like this, because later we discovered, after we'd already given it the name beta, that it was just an electron. So sometimes we write the symbol like this, where the atomic number normally goes, which is the number of protons, we write -1. What? How can you have -1 protons? Well, that's basically what we're calling an electron, since it's got the same charge as a proton, just the opposite. So the -1 means 1 electron, and the 0 is the mass number there, because there's not any protons or neutrons. It's just 1 electron there. So we've already practiced alpha decay, and beta decay is pretty similar rules. So let's do a few of those, keeping in mind that the neutron becomes a proton, which stays in the nucleus, and the electron is shot out at high speed, known as a beta particle. So let's do our first one right here. And let's begin like this. Let's say we've got polonium, which has an atomic number of 84, so 84 protons in polonium. And let's say this particular type of polonium, it's an isotope 216, so 216 protons and neutrons in the nucleus. Let's say that this undergoes beta decay. So that means we're going to spit out a beta particle. So we'll write this, the symbol for a beta particle. So here's the electron that gets shot out. So what is the other nucleus left over? Well, let's look at our mass number. Remember, this is the total number of protons and neutrons together. Well, a neutron died, so to speak, but it became a proton. So we didn't actually lose anything in our mass number. Yeah, a neutron left, but we gained a proton, so that stays the same. What about here? Well, a neutron became a proton in this electron, so this number actually goes up. And so now we're up to atomic number 85. 85 protons. So you have to look up in your periodic table, unless you've got this memorized, and see who has atomic number 85, and it's astatine. So that is symbol AT there. Get out, astatine. And so that is our completed example of a beta decay equation. By the way, sometimes, again, you will see in some books, instead of writing as an E that way, you might see some books write it like that. So same thing, instead of E for electron, it's B for beta particle. Either way, they're both equivalent. So this brings up a few beta decay rules here, like we had alpha decay rules. The first one, let's look at the mass number. So if we look at the mass number stays the same. So 216 here, 216 here. And again, that's because the total number of protons and neutrons doesn't change when a neutron just changes into a proton. So here is rule number 2. No, kitty, I can't play with you right now. I'm making a video. All right. So the second rule is the atomic number goes up by 1 because a neutron changed into a proton. So from 84 to 85 right there. So let's do a few more examples, keeping these beta decay rules in mind as we go through it here. So let's clear this one out and let's do another one. Let's say, because when you finally go to do the homework on this, you might be given an example and they don't tell you if it's alpha decay or beta decay. So how could you know? So let's say you see this. TH is thorium, named after Thor, the god of thunder, and it's got atomic number 90, and let's say this isotope has a mass number of 234. And then you see this. You see that it becomes PA 91 234. Who's PA? It's our old buddy protactinium. Remember him from the alpha decay? So how could you tell whether or not this was alpha decay or beta decay? So we would look at two things, two clues here. One is the mass number stayed the same, so we don't see any change in that. And one is that the atomic number actually went up by 1. So we got to account for that here by putting a -1. And so that lets us know that it must have been beta decay. So again, notice the equation basically holds. 234 is equal to 234 plus 0. And 90 is equal to 91 plus -1 there. All right. Let's try another example. Let's do another one of those where we begin with what's going to undergo beta decay, and we know that it's going to be beta decay. So let's say we have iodine, which is atomic number 53, and let's say it's got a mass number of 131, like this. So, and they tell us it undergoes beta decay, like that. So what is the other nucleus going to be? Well, let's figure it out. Remember, the mass number isn't going to change. So that will stay 131. And then the atomic number's got to go up by 1 because we gained a proton. So that's got to be now atomic number 54. 54 protons. We got to look up in our periodic table to see what that is. And it's xenon. Xenon has atomic number 54, and its symbol is Xe. And besides being an element, xenon was also a low-quality show about a warrior princess in the late 1990s there. Okay, one more quick example here, and then you will be on your merry way. So let's do one. Let's say they told us everything we had in the end and asked us what we had in the beginning. So they told us that we had some type of beta decay here, and that what we were left over with was a mass number 52 and atomic number 26, which is iron. So what could have given us a beta decay that winds up with iron? Well, remember the mass number can't change. So that's still got to be 52 over here on this side. And this had to go up by 1, right? What is 26 plus -1? That's 25 because one of our neutrons became a proton and went up to 26. So we got to look in our periodic table, see who atomic number 25 is, and it's manganese. When someone says manganese, you got to say Gesundheit. So manganese is atomic number 25, and we've completed our equation.